All right, so here we are. Today is section 2.6, and we are we're talking all about exploratory data analysis so far in chapter 2. And at this point in chapter 2, we're talking about 2 quantitative variables. And last time we talked about graphs and numerical summaries for 2 quantitative variables. And today we're going to take it one step further. So kind of to sum up, the very first thing that we always do with our set of data when we're examining it is to graph the data. The second thing that we do is to calculate numerical summaries. And pretty much with all the other scenarios, this is basically where it ended. We talked about graphs, we talked about numerical summaries, and then we're like, hey, that's great, and we moved on. But when we're talking about 2 quantitative variables, which is what we're talking about now, we are going to take it one step further, and we're going to learn how to model the data. So with 2 quantitative variables, like we've been talking about, what's the graph that we talked about last time that helps us look at the relationship between 2 quantitative variables? What's the name for that graph? You can type it in the chat window. Yeah, a scatter plot. So scatter plot is the graph that we're going to look at. We're going to look at the relationship between 2 quantitative variables. And if you remember from last time, we're looking for 3 things on that scatter plot. And unfortunately, I haven't thought of any clever acronym to remember those 3 things like there is to remember with histograms and dot plots. Does anybody remember the 3 things that we're looking for on a scatter plot? Okay, form, perfect. Form is the first one. Direction is the second one, and strength. So form, direction, and strength. So once we've looked at our scatter plot, if we decide that it has a linear relationship, then we can take it to step number 2, the numerical summaries. And what's the name of the numerical summary that we use to describe the strength of the linear relationship between X and Y? What do we call that? Yes, correlation. So correlation describes the strength of the linear relationship between X and Y. And when we're talking about correlation from sample data, who remembers what the notation is when we talk about correlation from sample data? R, yes, little lowercase r. And then when we're talking about population, we use the Greek letter rho. So we're going to look at correlation. Last time we talked about several different characteristics of correlation. We said correlation is going to be a number between -1 and +1. And the closer you are to -1 or +1, the stronger the relationship. And then the closer you are to 0, the weaker the relationship. The sign on correlation just indicates the direction and not the strength. So the strength we can get, if we look at the absolute value, then the closer you are to 1, the stronger it is. And then again, the sign just indicates whether it's positive or negative. So if we have a positive relationship, then as X increases, Y also increases. So X and Y are doing the same thing together, either both increasing or both decreasing. And if we have a negative relationship, then X and Y are doing opposite things. So as X increases, Y decreases, or if X decrease, then Y would increase. So negative relationship, they're doing opposite things. We did also mention last time that correlation is not resistant, so it's going to be affected by outliers. In fact, it's highly affected by outliers, which is another reason why we always want to plot our data first so we can be aware of if there's outliers there, and we can try to figure out how much exactly they are affecting our analysis. All right, so once we've graphed it, we've calculated the correlation, then we're ready to move on to step 3, which is going to be to model the data. And since we're looking at linear relationships here, then the type of model that we're going to use to model the data is a line, like a linear, obviously a linear line. That's like, sounds redundant, sorry. Okay, so what we're going to use is something called the least squares regression model. So regression really just means the line. Okay, so when we talk about regression lines, then we're talking about our linear model here. Okay, the regression line is it models the linear relationship between 2 quantitative variables. So when you hear people talk about the line of best fit, That's basically what our regression line is. So it can also be called the line of best fit. And specifically, the type of regression line that we're going to be using in our class is called a least squares regression line. And I'll show you a little bit later exactly what that means. But I'll kind of define it here. Don't worry too much about the definition for least squares and what least squares means exactly, because in our class, the only type of regression line we're going to look at is a least squares model. So it's not really that important that you understand why it's called the least squares regression line. Just know that this is going to be the line of best fit. This is going to be the line that fits the data really well. That's as close as possible to all of the data points. But I will define it here for you. So least squares, which is what we're looking at, regression line. It makes the sum of the squared distances from the line as small as possible. So again, all we're really saying here is it fits the data really well, and even though it kind of has a complicated sounding explanation, one of the reasons why we actually like the least squares method is because it does have a pretty simple way to come up with the parameters for the line. And in our class, it's going to be even easier. We're not even going to use the formula to come up with the parameters for the line. We're actually just going to use software like StatKey to come up with the different values for our model anyway. Okay, so here is what our regression model looks like. We're going to have y hat is equal to a plus bx. So x over here, that's just going to be our explanatory variable. And then y hat is the predicted response. So one of the purposes for creating this model, creating this regression line, is going to be to make predictions. So we're going to want to be able to input a value for x and then have the model tell us what it would predict that y would be. So we call that y hat. Basically, anytime we put a hat on something in statistics, then we're talking about a predicted value or an estimated value for that value. So when we talk about p hat is estimating p, so it's an estimated value for p. So those are the most basic parts of the model that you probably already understood. Now, if you look at this model, a plus bx, it should look fairly familiar to you from back in algebra, only in algebra you use different letters. You didn't use a and b, you might have used m and b instead. So hopefully that looks a little bit familiar. It's basically just the slope-intercept form of the line. So in algebra, you probably said y equals mx plus b, and in statistics, we're going to say a plus bx. So the b actually represents different things in algebra than it does in statistics. So don't get those confused. So let's break down a little bit more what the a and the b are. So the b is going to be the slope part of our model. And slope is a rate of change. It tells us for every 1 unit increase in x, we expect y to change by b. Okay, a is my intercept. So the intercept value is the value that we would predict for y if x was equal to 0. So I do have those written down here. So slope, that's b. Okay, slope is going to be the one that's attached to the explanatory variable. It's a rate of change, and it's the increase in the predicted y value for every unit increase in x. And then the intercept, so hopefully you write these things down even though I'm not typing them out for you. Intercept is the predicted y value when x is equal to 0. So if x is equal to 0, you would end up with y hat is equal to a. Now, as far as when we put this in the context of an actual problem, the slope is going to be the most interesting, coolest part of our model. Okay, the slope is always going to be an interesting part of our model in the context of a problem because it's actually going to quantify the relationship between x and y. It's going to give us an actual number. It's going to say, hey, for every 1 inch increase in your height, we expect your weight to go up by 6 pounds. So it's going to give us a quantification for that relationship. So slope is awesome. We love the slope. Intercept, on the other hand, is only sometimes going to make sense in the context of the problem. And it's basically only going to make sense in the context of the problem if having x equaling 0 makes sense. So if I'm talking about height and weight, Well, do you know anybody that's 0 inches tall? No. So interpreting the intercept as a value really isn't going to make sense. Okay, we have to have the intercept to make the model work, but as a value in the context of the problem, it's only going to make sense if it would make sense to have x equaling 0, which in many times it doesn't. So the intercept is like the less important term in the model, and the slope is like the super important term in the model. And I also want to point out that in your textbook, they like to write the model like this. So instead of using X and Y, they like to actually put in the name of the response and explanatory variable. So it kind of just helps put it into a little bit more context. But I just want to make you aware that you're going to see it both ways. And in fact, on the next example we do, you're going to see it written this bottom way, where we're actually going to have the name of the response variable there under the hat symbol, and then the name of the explanatory variable over here. All right, so let's look at an example. We want to figure out if we can do crickets chirp. So what researchers did is they went outside on several evenings in the summer, and they listened to all the crickets, and they counted the chirp rate, which was the number of chirps per minute that the crickets were chirping. Okay, and then they also measured the temperature outside, and they tried to see if they could, well, they tried to look at the relationship and see if there was a relationship between the chirp rate and the temperature outside. So what's the very first thing that these researchers should have done with their set of data? They collected it, they're ready to go. What's the very first thing that we always do with our set of data? Graph it, exactly. So they did a graph. They're going to do a scatter plot because we're looking at 2 quantitative variables. And this is what they got for their scatter plot. So remember, we're looking for form, direction, and strength. So let's start with form. What kind of form does this scatter plot have? Linear. Definitely looks like a linear. It would pass the fat hot dog test. In fact, it would probably pass the skinny hot dog test. It looks pretty good. Okay, what about direction? Positive. So as the chirp rate increased, so did the temperature outside. So it seems like those crickets are chirping a little faster when it's warmer outside. And what about strength? Yeah, this one's like super strong. I mean, these points are almost lining up perfectly on a straight line. So this is really strong relationship based on the data that we have here. All right, so first step would be to graph the data here. And once we see that it looks like there's a linear relationship, then it would be appropriate to calculate the correlation. So inside of, oh yeah, there's the explanatory and the response variables. Inside of stat key, over on the side, so you have your scatter plot on one side, and then on the right-hand side of the screen, then it gives you all this summary data, including the correlation. So for this data, it tells us that the correlation is 0.991. And 0.991 is super close to 1, which would, again, just like we saw in the graph, indicate we have a very strong positive linear relationship between chirp rate and temperature outside. All right, so once we've graphed it and we've looked at the correlation, we're ready to model the data. And you can see down here, in fact, I think I have it on the next slide, that they give you the slope and intercept for the regression line inside of StatKey. So all we have to do is put that into equation form. So this is what it looks like when we write out the regression equation or the regression model. So predicted value for temperature, because temperature was our response variable, is equal to 37.7 plus 0.23 times chirps. So let's talk about these different parts of the model here. Okay, first of all, let's look at the intercept, this 37.7. Okay, remember, if we're interpreting this value, what that would mean is that if chirps was equal to 0, then we would expect the temperature outside to be 37.7, which kind of probably doesn't make sense in the context of this model. And if we look back at our scatter plot, we can see that really the data was only collected between about 80 and 200 chirps. So thinking about a chirp rate of 0 it's probably not really going to make sense in the context of this problem. So as a number, the 37.7 is kind of meh. It's not really that interesting to us because it doesn't have a lot of meaning in the context of this problem. But let's look at the slope. Remember, the slope is our favorite part of the model because it is going to quantify the relationship between X and Y, between the chirp rate and the temperature outside. So this 0.23, what that means is that for every 1 chirp increase in the chirp rate, we expect the temperature outside to increase by 0.23 degrees. So I have that written down here on the next page here. Okay, so slope, to interpret that, what that slope equals 0.23 means is for every 1 chirp increase in chirp rate, we expect the outside temperature to increase by 0.23 degrees. All right, and I also have the intercept on here, but again, the intercept was kind of meaningless in the context of the problem here, just because we really don't know what happens when the crickets stop chirping. So thinking about a chirp rate of 0 doesn't really apply in this case. Being able to correctly interpret the slope of our regression line is going to be really important in our class. And when we're talking about interpreting the slope, it needs to be very specific. So sometimes I ask people to interpret the slope and I get answers like, oh, it's positive, or oh, as X increases, Y increases. And while the slope does tell you that, it tells you so much more. So when I want you to interpret the slope, I want all the details. I want variable names, I want units, I want the value of the slope and how the value actually applies to the context of the problem. So what I have for you here is kind of a formula or a pattern that you can use to write your interpretation for the slope. And I'm definitely going to be asking you this on tests, on homework. So put it down, write it. If I was you, I'd put it on your cheat sheet for the exam. I'm going to put a bunch of stars around it on here so you can see just how important this is going to be. So in this little pattern or formula that I have here, all the red parts are things that you're going to fill in specific to the problem that you're working on. And then the black parts are going to be the ones that stay the same no matter what. So we can kind of see how I did this for the chirp problem that we're looking at here. So for our chirp problem, we were measuring chirp rate. That was our explanatory variable. And chirp rate is measured in chirps or chirps per minute. And then our response variable was the outside temperature measured in degrees. So when I wrote the interpretation, I said for every 1 chirp, because chirp was the unit for the explanatory variable. So for every 1 chirp increase in chirp rate, my X variable, we expect the outside temperature, my response variable, to increase by 0.23 degrees. So 0.23 is my slope, degrees is the units for my response variable. And I would choose increase or decrease here in the last part of my interpretation, depending on the sign for my slope. In this case, slope was positive, so I'm going to choose increase, and if slope was negative, then I would choose decrease. Okay, so this is data that was collected on vehicle weights measured in pounds and the vehicle's gas mileage in miles per gallon. And you can see the regression equation is right up here on the top of the graph. So it's mileage or predicted mileage is equal to 45.57 minus 0.0051 times vehicle weight. All right, so what I want you to do is just on your paper, see if you can use the pattern. I put the pattern up there to write out an interpretation, and then we'll look at it. We'll see if you got the right thing or if you got the same thing that I did. So I'll give you a minute or so to write that down. All right, let's talk about what you got here. So the X variable was vehicle weight. It was measured in pounds. The Y variable was mileage measured in miles per gallon. So you should have gotten something like this. For every 1 pound increase in vehicle weight, we expect mileage to decrease by 0.0051 miles per gallon. So this one was decreased because our slope was negative. So how did you do? Thumbs up, thumbs down? your window? I see, okay, good. I'm seeing lots of thumbs up. All right, so like I said, I recommend writing that little pattern for writing the interpretation down on your cheat sheet. There's some other ways that you could write it. It doesn't have to word for word be exactly like this. But if you're at all worried about doing it right, then I would just follow my pattern and then you'll be all set. You can kind of, and I think on Wiley Plus, they might kind of switch the order of things. Like we could say, we expect mileage to decrease by 0.0051 miles per gallon for every 1 pound increase in vehicle weight. So you see how I've like swapped the beginning and end of the sentence, and you can totally do that and it's still correct. But until you kind of really understand what it is and everything, then I recommend just using my pattern. So one of the things that we can do with our regression equation, once we have it, is we can use it to make predictions. So if I tell you a value of X, then you can use that to predict the value for Y. So for example, if you go outside in the summer and you listen and you hear crickets chirping and the chirp rate is 140 times per minute, then we could plug that into our formula here to figure out what we think the outside temperature is. And all we're gonna do really is exactly kind of what it sounds like. We're just gonna take this 140 and we're gonna plug it right in here for chirps. So if you have your calculator, go ahead and do that with me. So we're just going to take 37.7 plus 0.23 times 140. So I'm just plugging that 140 in for X. Okay, perfect. Everybody's getting the same thing over there, and it's 69.9. So I'm just taking the 37.7 plus 0.23 times 140, and it gives me 69.9. So it's going to be about 70 degrees outside if we hear the crickets chirping about 140 times per minute. So notice the order of operations here. You're going to do this multiplication before you do the addition. Okay, so here's another one. What would be the predicted temperature when the crickets are chirping at 103 chirps per minute? So try that out and see what you get. Okay, perfect. So we get 61.39 when you plug that in. So basically you can make predictions for any value of X. You give me an X value, all we have to do is plug it in. We can get a predicted value out of that. So last year, I don't know if you guys remember, well, you probably remember when all those disgusting crickets were all over the place in October. And they were everywhere. So the picture on the right here, this is a picture my daughter took when she went to get gas and she was afraid to get out of her car because there's so many crickets everywhere. She's like texting me from her car, do I really need gas that bad? The other picture is one that I just took at ACC because they were all over. I don't know what campuses you guys were at, but at Cypress Creek campus, then they were all over the floor. I'd be teaching. They would like fall from the ceiling onto the desk. Like it was so nasty. But we had just barely talked about this example in class, and so we decided to test it out because we had all these crickets in the classroom. So we're like, hey, let's try it out and see if it actually worked. Let's try out our model. So we did. So we sat there, we all listened to the crickets chirping, we counted the chirp rate, and we used it to predict the temperature, and then we went and found the temperature thing so we could figure out exactly what temperature it was in the classroom. And guess what? It was actually right on. So the model totally worked, like in our own classroom. So that was the upside to having all those disgusting crickets hanging around. Okay, so we talked about making predictions. The next thing that we can do with our model is we might want to actually plot that regression line onto our scatter plot. And I'm going to back up for just a second here. So here's my scatter plot, and I want to be able to put my regression line onto this graph. But if you remember back to algebra when you were plotting lines, then a lot of times you could just find the y-intercept, and then you could just use the slope to kind of plot your way through the graph. So in this case, we would have to find, like our model was 37.7 plus 0.23 times chirps. So using like your algebra method, then you might find 37.7 on the y-axis and then go over 1 up 0.23 over 1 up 0.23. But if you look at my graph here, is that method going to work? it's not going to work. Because first of all, my axes, most of the time on these graphs, they don't start at 0, 0, because a lot of times the data that we're dealing with doesn't even make sense to talk about zeros. So I'm not going to be able to find the y-intercept. And even if I could find it, then going over 1 up 0.23 is really tricky to make that accurate. So using the algebra method to draw our line on our graph is not going to be a good method. So we're going to have to do something else. So instead, what we're going to rely on is the idea that if I could get 2 points to on my regression line, then if I connect those 2 points, then I could actually create the line on my graph. So that's what we're going to do instead of the traditional algebra method. Okay, so I'm going to write down the instructions for how we're going to plot the regression line onto our graph, and then we're actually going to try it out. So plotting the regression line on the scatter plot. And your book is not very descriptive about this, so if you're looking for more help in the book on this topic, you're probably not going to find it in there. Okay, so the first thing that we're going to do is we're going to pick 2 x values, any 2 x values. Now, I recommend looking at your scatter plot and just choosing 2 of the x tick mark values that they have on the plot. Only because when you go to plot it later, it's going to be easier if there's already a tick mark that you can just go off of from there. So when I do it, I just look at my x-axis, I pick 2 of the tick marks. I try to pick tick marks that aren't right next door to each other so that it's a little bit easier to draw a line. My points are going to be a little bit farther apart, for example, but really you can pick any 2 x values that you want to. Then we're going to plug both of those x values into our regression equation to get 2 predicted y hat values. Okay, what this is going to do is now we have 2 ordered pairs that came from the regression line. These 2 ordered pairs are different from our actual data points. They are not actual data points. They're just values that came from the line itself. So the next thing is I'm going to do is I'm going to plot those 2 points, those 2 ordered pairs onto my graph. So plot the 2 ordered pairs on the scatter plot. And then I'm going to connect those dots to form the regression line. All right, so let's look at how we would do that for this exercise. All right, so here is my scatter plot. So I'm just going to follow the steps to plot the regression line onto my graph here. And so the first thing I'm going to do is I'm going to pick 2 values of x. And like I said, I like to look at my x-axis and just pick 2 of the tick mark values on the x-axis. So looking at my x-axis, anybody have any preferences? Which one that they would want to choose? Okay, 100 and 160. Those sound like good ones. So let's choose those. I'm just turning on my pen here. Okay, I like to make like a little table with mine too. So I'm going to make an x and a y hat, and I'm going to put that together in my little table here. So the 2 x values we've chosen are 100 and 160. So remember, we could have chosen 120 and 180. We could have chosen 80 and 180. We could have chosen 120 and 160. Like, you could even choose one in between. You could choose 150 if you want to. It's just easier, I think, if you choose a tick mark value rather than one of these that you have to kind of estimate where it is when you're plotting it later. Okay, now I have my 2 x values. Now I'm going to plug those into my regression value. Okay, question in the chat window, do the x values you choose have to be a plotted value or just any value on the graph? Any x value. You're choosing any x values. In fact, when you're plotting this line on the graph, we're actually ignoring the actual data values that are there because the line drawing the line is not based on where these dots are, if that makes sense. So you choose any 2 x values regardless of whether you had an x value like that in your data set. Okay, so now I'm going to plug these 2 x values in. So for my first one, that means I'm going to have y hat is equal to 37.7 plus 0.23 times 100. So that's just plugging that x in right over here. So 37.7 plus 0.23 times 100. So for that one, I get 60.7. So I'll write that over here on my chart, 60.7. Now I'm going to do the same thing with my other x value. So I'll have y hat is equal to 37.7 plus 0.23 times 160 this time. And I get 74.5. All right, so now I've taken these two x values that I've chosen, I've plugged them in to get two y hat values. So I have two ordered pairs that actually came from my regression line. So again, these are not values from my data set. These are independent of the values in my data set. These are actual points that would fall exactly on that regression line. So I'm going to plot these two ordered pairs and then connect them, and that's how I'm going to get my line on my graph. So starting with the first one, it's x of 100 and y of 60.7. So I'm going to come over here to x equals 100 and up to 60.7. And I like to make a little x rather than a dot, just because the x reminds me, hey, this isn't a real data point. This is just a point from the line. So I don't want to get it confused with any of these other dots that are on the graph, because those dots, the black dots, those are all real data points. And right now we're not plotting a real data point, we're just plotting a value from the line. Okay, my second one is 160 and then 74.5. So that's going to be about right up here. So I'm going to put my x there, and then I'm just going to connect those dots. So if you're doing this on your paper at home, you could get out a straight edge. That would give you a nice, pretty, lovely looking line. And here I am trying to draw this on the computer screen. So my line's probably not going to be that lovely, but I'm going to do the best that I can to draw through those 2 points. So here I am. And the line, remember, it doesn't start and end where I have my x's. It keeps going and going and going in both directions. So these just happen to be the 2 points that I found on the line, so I know where to put the line, but the line itself extends in both directions. All right, so now I have my regression line plotted on my graph. All right, so I have my regression line on my graph. So why would I care about having it on there? Well, first thing, of course, it looks cool on there, and it's kind of nice to see where that line of best fit is. And another thing is that we can actually use the line to make predictions. So first, I do have a computer-generated line on my next slide. Hey, look at that. I did pretty dang good at getting my line on there. My x's actually went right through the real one. Okay, so let's talk about how we could use the line to help us make predictions as well. So we've used the equation to make predictions, and using the equations is actually going to give you the most precise predictions. So it's great to use the equation. However, like let's say you're going to a party this weekend, the party's outside, and you want to impress all of your friends with your ability to predict the temperature using your Cricut model. But you don't want to carry around a calculator in your back pocket because that would be so nerdy. So instead, you're going to carry around this graph in your back pocket, and then you don't have to have the calculator, because carrying this graph is not nerdy at all. So you put this graph, it's in your back pocket, you go to the party. While you're at the party, you're listening to the crickets and you're counting how many times they are chirping. And let's say that they are chirping 160 times a minute. Okay, so then you whip out this graph from your back pocket. You come over here to the x-axis where it says 160. You go straight up from 160 to the line. When you get to the line, you're going to go straight over to the side. All right, and wherever it crosses the x-axis would be your predicted value for the temperature. So in this case, if we're looking at 160, then we're looking at about 74 degrees outside. So this is when, you know, like I said, you can wow and amaze your friends, because you'll be like, I am predicting, I'm estimating that the temperature out here is 74 degrees. And then they'll go look on their temperature thing and they'll be like, wow, you're so amazing, you're so smart. Okay, and you were able to do this because you had this regression model in your back pocket. So we can use this for any value of X to give us a pretty close estimate for what Y would be. So if I wanted to estimate 140, for example, then again, I'm just going straight up from my X value, take a left turn all the way over to the Y axis, and that's going to give me an estimate for my temperature outside. And as you can see, remember when we actually plugged in 140, we got 69.9, and that's pretty much what we get, the same exact thing that we're seeing here when we look at it visually on the graph as well. Okay, so here's a chance for you to practice this out. So if the crickets are chirping at about 180 times per minute, what do you think your best guess for the temperature would be? Okay, C80. So yep, if we come up straight up from 180 and over, then we're gonna get pretty close to 80, maybe around 79 degrees with the crickets chirping. It's like a tongue twister. One thing with our model, if we're using it to make predictions, and especially if we're trying to wow and impress our friends at our party this weekend, then we are hoping that our model is making accurate predictions, right? We're hoping that the prediction is really close to the actual value. And if you look at this data here, these points, they fall pretty close to the line, which means that we're probably going to be getting some fairly accurate predictions out of this model. So to kind of understand whether or not our predictions are going to be accurate or how accurate our predictions are, really, we look at the distance from the point down to the line. Okay, so like in this case here, the line says, hey, this is what our model predicted. The actual data point says this is what we actually saw. So we're going to look at that difference, you know, how different they were, the predicted and the observed value. So one of the cases in the cricket data set had 103 chirps per minute, and the actual Y value for that, the actual temperature, was 63.5 degrees. So what we want to know is how far is that predicted temperature from the observed temperature for that case. Okay, so if we do that, we already plugged in that 103 before, so we know that the line would have predicted that the temperature was 61.39 degrees, but actually, in real life, for that data point, the temperature was 63.5, so that difference is 2.11. And we're going to call that difference the residual. We'll write down that definition in just a second, though. Here is that data point we were talking about. Okay, the actual Y value was 63.5, but our line would have predicted 61.39, I think is what it was. So there's our predicted values down here on the line. And that difference between the point and the line, or that distance from the point to the line, is 2.11, and it's what we're going to call the residual. And when you think of residual, you probably think of like leftover, and that's basically what it is. It's like the leftover variation. So our line said it should be this, it was actually this, so this is like the leftover amount of variation that our model couldn't account for. So write this down. A residual for each data point is calculated by taking the observed Y value and subtracting the predicted Y value. So in general, sometimes you're going to get like in a problem or something, like in your homework, then they might tell you, okay, here we observed this value. Here's the X and Y values for this observed point. Okay, so this is our observed point. Okay, and then they're going to give you the regression equation and they're going to say, find the residual. Okay, well, from this observed point, that's where this observed Y value comes from. So it's going to be given to you. It's a point that was collected in your data set. So the Y is given. It's going to be given to you. Now this Y hat value, what we're going to do is we're going to take the observed X value and plug it into the regression equation to get our Y hat value. So take the observed X value, plug into regression equation, to get y hat. So we're going to take this X, plug it in to the regression equation, and then it's going to give us a y hat value, and that's the y hat that we're looking at here to compute our residual. So we always take observed minus the predicted, so y minus y hat, and not the other way around. So this residual is also the vertical distance that each point is to the line. And we can compute a residual for all the data points. So for every point in our data set, we can find out how far it is from the line. So if you remember, back in the beginning of class, we were talking about this least squares regression line. And basically, this is where the idea of least squares comes from. It's the line which minimizes the sum of the squared residuals. So these distances from the point to the line, if we find all those distances, square all the distances, this is the line that makes the sum of all those squared values as small as possible. And again, if that makes no sense to you, don't worry too much about it, because I don't really expect you to understand that. But in case you have an inquiring mind and you want to know, here's kind of a visual of what that would look like. So you have all these distances, we're going to square those distances, and then we're going to make the sum of all those values as small as possible. But again, what that means in practical use is that this is a line that's basically as close as possible as it could be to all the points. Now, just because it's as close as possible to all the points, that doesn't mean that it will necessarily go through any of the points. So most of the time, none of the data points are actually going to fall on the line. The line's just going to be as close as possible to all the data points, if that makes sense. Okay, so I'm going to take a quick second to just jump over into StatKey so I can show you how to get the regression equation, how to put the regression line on the plot over in StatKey. And we'll kind of use that as we talk about the next section, which is going to be cautions about regression. Okay, so here I am in StatKey, and we've been talking about two quantitative variables. So over here, I'm going to choose two quantitative variables if I want to look at a scatter plot and figure out the regression equation and all that good stuff, which of course I do want to figure that out. So here I am in two quantitative variables, and I'm going to look at the data that we collected last time for our Scrabble values. So remember, everybody figured out the number of letters in your name, and then you also figured out the Scrabble value for your name. So here is that data that we collected last time. So I'm going to copy and paste this data over so we can look at it. So just copying it. Then in here, remember, if I want to paste it in, I'm going to click on Edit Data. I'm going to get rid of everything that's already in there. So clear that box out, and then I can paste in everything that I copied from my spreadsheet. So this is something that you're either going to need to paste the data in or upload the file in your homework, your written homework this week, in order to do that. Okay, once I've got the data in there, I clicked on OK. We looked at this a little bit in class last time. We decided that the form was mostly linear, but a little bit banana shaped over here. Like it seemed like it was going to be linear, and then it seemed like over here we had a little bit of a flattening, almost looking like a banana. So a little bit of slight curvature there. We said the direction was positive. It does seem like in general, as the number of letters in your signature increased, so did the Scrabble value for your signature. And the strength we said was kind of moderate, especially because it does have a little bit of that curvature in it. So looking over on the left here, you can see it tells us the correlation 0.658. That also indicates moderate relationship there. And underneath here, it's giving us the slope and the intercept. So on your paper, write down the equation for the regression line for this data. If you can write it down, and then I'll write it down. We'll see if you you got the same thing. So just given this information, slope and the intercept, you have the graph, so you should be able to figure out the x and the y variables. Then write down the equation for the least squares regression line. All right, looks like everybody's had a chance to get something written down there. So let's go ahead and write it down on here. So when I'm writing this, remember I can use y hat or I could use the actual variable name. So I'll use y hat. If you put, the y variable was the Scrabble value. So if you put Scrabble with a hat over it, that would also totally work. So I'm gonna have y hat is equal to, then I'm gonna put my intercept. So my intercept is negative 0.867. So negative 0.867. And then my slope is positive 1.859. So I'm going to say plus 1.859 times x. And instead of x, if you put signature or name or something like that, then that again would also be totally fine. So this is the equation for the least squares regression line. So my intercept, negative 0.867, we're saying, well, if I had 0 letters in my name, then I would expect to get negative 0.867 points in Scrabble for that. Again, you know, we're not really that interested in names that are 0 letters long, so interpreting the intercept is kind of bleh in this case, doesn't have a lot of meaning in the context of this problem. But the slope always has great meaning. Okay, so see if you can write down on your paper how you would interpret the slope for this regression equation. So remember, you can use that little pattern, the one that I put all the stars around earlier in class. All right, I'm going to put my answer over in the chat window, and you can check your answer with my answer and see if you got something similar. So I said for every 1 letter increase in your signature, we would expect the Scrabble value to increase by 1.859 points. Okay, so let's go back and start talking about some of the cautions that we have to worry about when we're dealing with regression. Remember, we talked about cautions for correlation. Now we're going to talk about cautions for regression. Some of them are going to be a little bit similar. So the first one here, first caution, is that unlike correlation, it does matter which variable you call x and which one you call y. So unlike correlation, it does matter which variable you call x and which one you call y. Remember, with correlation, either way you called it, you're going to get the same number out. For regression, you're going to get a different line if you switch the order of the variables. Okay, the second one, so the second one is like correlation. Regression is only going to model linear relationships. So regression only models linear relationships. So if you have a rainbow, a smiley face, you know, a banana, your model's not going to be very good because regression only looks at linear relationships. So any kind of curved relationship is not going to work with our regression model. Okay, my third one is that extrapolation can lead to inaccurate predictions. So extrapolation can lead to inaccurate predictions. So some of you might be wondering, what does extrapolation mean? Extrapolation is trying to use your model to make predictions for x values that are outside the range where your data, where your model was created. So for example, let's say that we were looking at height and weight, and that I took everybody in our class and I created a model to be able to use somebody's height to predict how much that they weigh. So I based it off of all of you guys, college students. And so let's say I take that model over to my sister's house, and my little niece over there is 2 years old. So if I plug in my niece's height, do you think it's going to give me a good prediction for how much my 2-year-old niece weighs? No, it's going to give me a terrible prediction, right? Because my model was based on college students, so I can't go trying to apply it to toddlers because that, you know, my model wasn't based on using toddlers. We have no idea what the relationship for toddlers' height and weight is. So it's not going to be represented or accurately modeled by my model. So that's what we mean by extrapolation, like trying to make some kind of prediction for a value that's way outside the range of values where my model was created. Okay, someone says, if a regression line predicts that there is no slope, then would it still be considered a regression line? So if you end up with a slope equal to 0, then on your scatter plot, you should have seen a blob. Okay, and if there's a blob, then looking at a linear relation, a linear model is no good for that either. Okay, so my third one, extrapolation. Let's talk about the fourth one. The fourth one is that even a strong linear fit does not imply a cause and effect relationship. So even a strong linear fit does not imply a cause and effect relationship. Okay, so it doesn't matter how pretty our scatter plot is, how amazingly our line fits the data. The only way that we can show a cause and effect relationship would be if that data came from what? What does the data have to come from in order for us to be able to conclude a cause and effect relationship? An experiment, exactly, a randomized experiment. Yep, the explanatory variable has to be randomly assigned in order for us to prove a cause and effect relationship. So number 5 is that regression is not resistant. So if it's not resistant, that means that it is affected by outliers. In fact, it can be highly affected by outliers. So we really have to be careful for outliers. And in particular, we have actually 2 different types of outliers, and regression is usually going to be more affected by one type of outlier than the other. So I'm going to say, in particular, watch out for special outliers called influential points, which exert an overly strong effect on the line. So watch out for special outliers called influential points or influential observations. So they're called influential points, and they exert an overly strong effect on the line. So let's talk for a second about a regular outlier versus one of these influential point outliers, and then I'm going to kind of show you how each of those things can affect our line. So the first one, a regular outlier. Okay, a regular outlier is going to have a point it's going to be an unusual point, but it's going to be a point that is unusually high or unusually low. So it's going to have an extreme Y value. So it's a data point that has an unusually high or unusually low Y value. So because of that, a regular outlier is typically going to have a large residual because it's going to be far away from the line. Okay, so those are going to be our regular old standard outliers. Next, let's talk about these influential point outliers. An influential point is different because an influential point is going to have an unusually high or unusually low X value. So thinking about horizontally along the X axis, it's going to have an unusual X value. And it's typically going to have a small residual because these influential points have so much influence on the line that they pull the line towards themselves. So if they pull it towards themselves, then their distance from the line is not going to be that far. All right, so I'm going to pop back over to StatKey so we can kind of examine the difference between these regular outliers and the influential points, and we can kind of see how much influence these influential points can actually have on our line. All right, so here I am in StatKey. First of all, notice that underneath over here on the right-hand side where it says scatterplot controls, if I click this little box, it will actually draw the regression line onto my graph for me. So that's pretty handy dandy there. All right, and let's say that there is this girl in our class, and her name, I had it written down, but where did I put it? But I don't have it handy, so now I can't tell you her name. Her name is like this ridiculous name where it's super long and every letter is only worth 1 point in Scrabble. Her name's like Elena Stravel. No, it doesn't have a V. A V would have a lot of them in there. Anyway, she has 32 letters in her name, and her Scrabble value is also 32 because every single letter in her name is all the really common ones, so they're all only worth 1 point. So if she was added to our class, and I can add her just by putting her values down here. So 32 and 32. I'm adding this crazy person to our class. Okay, so here she is right over here. Okay, so this girl, or she's a girl, I think, would be an example of an influential point, okay, because she has an extreme X value. Okay, now this person over here would be, or this person would be more of a regular outlier. Okay, so this is this one here. This is somebody that has a high Y value. Okay, but they don't have an extreme X value. By extreme, I mean different from everybody else. So if I look at this point here, you can see that there are other people that also had 15 letters in their name. There's people that had, a bunch of people that had 14 letters in their name, several people that had 16 letters in their name. So this person had an unusually high Scrabble value for having 15 letters in their name. This one is a regular outlier. This person out here, this is the only person that had 32 letters in their name. In fact, they're the only person that had more than 16 letters in their name. So they had twice as many letters in their name than anybody else. So this one is an influential point, okay? And in StatKey, you can actually move points around and it will show you how it affects the line. So it's kind of cool. So here's this value out here. And if I just move this one value up or down or over, whoops, it's kind of hard to control it though. I should warn you of that. Okay, I'm trying to get back out to my 32. Okay, but you can see that just moving it up or down, that 1 point, all the other points are staying the same, and moving that 1 point, I can completely change the line, right? So this 1 point, because it's way out here, has a lot of influence on the line. It can completely change the line. So that's why it's called an influential point, because it has the potential to be a huge influence on the line. Now these other values in here, like here is this one, the 1537, or even that one. Okay, this one had, it was away from the line, but because there's all these other values that are 14, 15, and 16, this one kind of has to share its influence with everything else that has a similar X value. So it's going to have less of an impact on the line. So you can see when I change this point, it moves the line a little bit, but not a ginormous amount like when I move this one. As soon as I move this one up or down, if I can make it move up and down, then you can see that it has like a really big effect on the line. And we can even change so that it has a negative slope and everything else. So this 1 point out there has a huge impact, whereas the regular outlier is going to have some impact, but not as much impact as those influential points. So that's why we're going to be like super concerned if we have an influential point in our data set about what to do about that. So what are we going to do when we have an influential point? And you're going to see this again in your written homework. You're going to be finding the influential point, and you're going to do this. So I'll go back and I'll tell you what we're going to do. So what to do when you have an influential point. Okay, what we're going to do is we're going to find the regression line with that point, and then we're going to find it without the point, and we're going to see how much it affects the line and how much it affects our correlation. And when you're doing this in StatKey, all you have to do is click on Edit Data, find the influential point in there, delete it, and then you can regraph the data, and it'll take care of that. So that's how you're going to be able to do it in your homework when you figure out which one that influential point is. Delete it, then see how it changes the slope, intercept, and the correlation. Here, if you want to be able to delete a point, so this was that wacky point with the 3232 that I kept messing around with. So I'm going to go in and delete that. All I have to do is click on Edit Data, and then I come down here and I find the point that I want to get rid of, In this case, it was that one, so I'm going to delete that. You can tell that it's also, these are the other points that I moved around, so they're not exactly right at the moment either. So you can delete or add points in the edit data anytime that you want to.